Swayam Prabha. Digital India. Educated India.
Okay, so you see, so we are continuing with the last kind of topic as far as the local theory of curves is concerned. Okay, see what we saw, namely the classification of curves. It is a local classification because you are only looking at curves defined on an open interval. Okay, and so you are basically looking at curves, uh, open arcs inside curves, all right, and you are not looking at a whole curve that is given to you, okay, as a whole. For example, you are not looking at a, let us say, something like a simple closed curve, all right. So you must understand that the classification is part of the local study, okay, and global properties of curves have to be done separately. Okay, so we will do that next. But there's one last topic in a local theory of curves, and that is the one that relates to what are called as evolutes and involutes and parallel curves. Okay, so this is the last topic in the local theory of curves. So let me write this: evolutes, involutes, and parallel curves. So we begin by recalling what the evolute of a curve is. So basically, you have a curve, and of course you assume it's a regular curve. Then at every point, you can look at the center of curvature at that point. Okay, so for every point on the curve, you have a circle of curvature and you have a center of curvature. Okay, and of course I am looking at only plane curves. Yeah, so this is very important. I am looking at only plane curves. Okay, so what is the evolute? The evolute is gotten by looking at the locus given by the centers of curvature. Okay, so you have a curve like this. Let us say gamma of t. Okay, and you give me any point on the curve. Let us say gamma of t naught, right? Then at that point, you have at that point you have the circle of curvature. Okay, and then you have also the center of curvature at that point. Okay, so basically, so if I draw a picture, it's like this. So you have this, so this is a circle of curvature at gamma of t naught. Okay, and of course this so let me write the gamma t naught on the other side. So okay, then of course if you join at the point to the center of curvature, this is going to be a normal to the curve. Okay, and then of course the tangent to the curve and the will be the same as the tangent to the circle of curvature at that point. Okay, and the thing is that you are looking at the locus of this, the locus of the centers of curvature as as t naught changes. Okay, and that is the that is going to be the evolute of the curve, okay, is the evolute of the curve, which we'll denote as epsilon sub gamma, okay, of t, okay. And so, but we have an expression for this, okay. Mind you, how do you write this? If there is an expression for this that we have already, we have derived this. So you see, this length is actually the the radius of curvature. Okay, so this is r gamma at t naught. This is the radius of curvature. At gamma of t naught, okay, and you know that this is the its reciprocal is the magnitude of the curvature, okay. So this is actually also equal to 1 by, if you take the sine curvature of gamma at t naught and you take its magnitude, that is what it is. And of course, when you are dividing by sine curvature, of course it is assumed it is not 0, right? So now how do you write this how do you write this thing? So you can write this thing using the sine normal and the sine curvature, okay. And that was initially that was the context in which even the sine curvature was introduced, okay. So the problem is that depending on the way the curve is turning, if you define the sine normal as gotten from the tangent to the curve by rotating it by 90 degrees in the counterclockwise direction, then the sine normal may or may not point towards the center of curvature. And when it doesn't point towards the center of curvature, you make the curvature negative, okay. And so that you can write, you can write this equation, namely, if you assume, so let me do the following thing. I want to be able to use the Frohn's-Array relations, okay, and so I should use a parameterization of the curve, which involves arc length, all right. But if I don't, I would like to use that if I want to make some deductions or write some things mathematically. But this can be done, you can, write this down even as it is. You see, how do you reach this point? How do you get the position vector of this point? So what you do is that, suppose I take some reference point as the origin. So let me remove this. So this is my curve gamma of t. See, suppose I take some reference point as the origin, okay, then this vector is gamma t naught, okay, and you see this vector okay, is the geometric normal, okay, which is taken as this radial segment, okay, from the point on the curve towards the center of curvature. The way this is expressed is actually it should be its length, which is the radius of curvature, multiplied by the unit vector along that direction, but that is adjusted to be that is written as 1 by the sine curvature times the sine normal. So you see, this vector here is written as 1 by ks gamma of t times ns gamma of t. Okay, that is how this is written. And you see, this is it's important to notice that if ns gamma, the sine normal, is pointing towards the center of curvature, then this ks gamma is positive, okay. And if it is pointing away, if ns gamma is ns, so in fact ns, I think we use a cap, so ns cap gamma, just to remind that this is a unit vector, all right. So if ns cap gamma is pointing away from the center of curvature, then this sign curvature you have to put a minus sign, okay, so that you always get this whole expression should point towards the center of curvature, okay. And of course, in this context, for example, in this picture, what happens is you see the t cap gamma at that point will be, the unit vector will be in this direction, okay, and you will see that the sign normal will be like this, which is gotten from this by rotating by 90 degrees, okay, in the counterclockwise direction. And you see that in this particular situation, the way we have drawn it, you see the unit normal is pointing away from the center of curvature. So in this particular situation, the sign curvature is actually negative, okay. So the net effect of all this is that you can write this vector, okay, which is so this vector can be written as, this is the position vector of the center of curvature is, you by triangle law you add gamma t naught to this expression, okay. This expression is 1 by ks sub gamma of t naught. So I of course that expression at t naught, so ns cap sub gamma t naught, okay. So this is the expression, okay. And of course t naught is varying, therefore I'll remove that subscript 0, okay. So this is the expression for the evolute, okay. And so the first thing one would like to understand is the following thing, that you see the first fact one would like to understand is that the evolute is the envelope of the normals to the curve, okay. So here is the first fact. So let me write it like this, and so fact, the evolute of the evolute E sub gamma of gamma is the envelope of the family of normals to gamma, okay. So you see, what is an envelope of a family of curves? It's another curve such that at every point it has the same tangent as a member of the family, okay. And if it is an envelope of a family of lines, it means that it is a curve at each point the tangent is a line from that family. So you see, when we say E gamma is the envelope of the family of normals, so basically you draw the normals, okay, and where the normals coalesce, okay, that's going to be the evolute, okay. And so for example, how does one see this? So let me give you a very simple picture. There is the picture of you take the picture of an ellipse, okay, and if you take this point on the major axis, okay, then the circle of curvature will be something like this, okay, and at that point, and you will get the center of curvature here, all right. And so this is going to be, suppose I call this point as P, then I'll have the, so suppose I call this point as P, then this is epsilon at P, okay, and the normal will of course go like this, okay. This will be the normal at P, all right. Now you see, and if I start moving from P to, let us say, this point Q, which is a point on the minor axis, what is going to happen is that I am going to get so the circle of curvature at this at Q is going to be large, okay. So it will be larger circle, okay, and you will get a point somewhere here, all right, and you will get this will be your epsilon of Q, okay. And what will happen is that so this is going to be the normal, this is going to be the normal at Q, all right. And as the point P moves from, as you move from the point P here to the point Q, along this line, okay, if you are moving like this, I mean along this along this segment of the ellipse, okay, then you can understand that you will for the initial normal is going to be NP at P, and the final normal is NQ at Q, okay, and what you will get is basically you will get something like this. So let me use a different color. So you will get uh, you will get a curve like this, okay, and this is going to be the evolute. This is going to be the segment of the evolute, and what is going to happen is, you see at this point, so this is going to be the evolute of, so if this is my gamma, this is going to be my evolute of gamma, right? And so in fact I'm in fact let me mark the correct segment. I am taking this portion, okay, so this is my gamma here, okay, right? And you see what is happening is that if you go all the way to the point Q, then that is a normal, and that normal is actually tangent to this curve here, okay. See, if you draw the full evolute, okay, you will get a non-symmetric asteroid, okay. So you will get, so if I I will just get, so let me just draw that. So for again, here I will get by symmetry, I will get this, and then here I will get so this is what is going to be the evolute, all right. And but what I want you to notice is that, you see, for the evolute E gamma at this point, you see the tangent to E gamma at P is NP. It is a normal to gamma, and the tangent to E gamma at Q is actually the normal to gamma at Q, and in between at every point the tangent to E gamma is actually the normal to gamma. So you see what will happen is that if you take a point here, then I will get normal like this, okay, and so this will be a normal, and then if you take another point like this, this will be a normal, and you see, so if this point is let us say P1, this is a normal at P1, and I will get this point which is epsilon of P1, okay, and for epsilon of P1, normal at P1 is the tangent to epsilon, okay, and of course epsilon is epsilon sub gamma, okay. The tangent to the evolute epsilon sub gamma at any point is actually the normal to the original curve, okay. So if you look at this picture, it is it's more or less clear that, you see, the evolute is the envelope of the family of normals, okay, and but then this has to be this can be verified, this has to be verified analytically, okay, and for that what you have to do is essentially use the Frones-Array relations, okay. So we can do that. So what we can do is that we can write, you see, so using the arc length as parameter, okay, what will happen is that epsilon gamma s will be gamma s plus 1 by kappa signed of gamma of s times n s sub gamma ns cap of s, okay. So this is going to be the equation of the evolute, okay, and first of all you need to know the fact that the normal to the to the original curve is actually the tangent to the evolute, okay. And so to understand that, what you do is, how do you get the tangent to a curve? You differentiate the curve, okay. So you apply d by ds, okay. If you apply d by ds here, I will get epsilon sub gamma dot of s, and here I will get on the right side gamma dot of s plus I have to differentiate this guy, okay. Mind you, this is a product of a scalar and a vector, but both of them are functions. So you have to use the product rule, okay? And remember that the scalar comes on the left side, okay? Scalar multiplication is on the left. So what you will get is, you see, I will keep 1 by ks gamma of s as constant. Of course, whenever all this is being written, it is assumed that the the sign curvature is not vanishing, okay? Otherwise I cannot write it in this form, right? And so I differentiate this, I will get ns sub gamma of s cap dot, okay? I will get that, okay? Where of course dot is applying d by ds, all right? Then by the product rule, I have to keep this vector constant, okay? And I have to differentiate this scalar, okay? So I will get minus 1 by ks gamma of s squared, okay? And I will get the derivative of that, which is ks sub gamma of s dot, okay? And I will get ns sub gamma cap of s. So this is what I will get. And you see, but now because I have used arc length as a parameterization, I can apply Frohn's array. So I can write what n dot is, okay? So n dot, t dot is kn and n dot is minus kt, okay? So this term will become gamma dot s plus 1 by ks sub gamma of s, and this fellow is going to be minus ks sub gamma of s into t cap sub gamma of s, okay? This is by this is equal to this by Frohn's array, okay? And then what I will be left with is this remaining term, which is which is here. So I will get minus ks sub gamma dot of s by ks sub gamma squared of s into ns cap sub gamma of s, okay? I will get this term, okay? And now you see that these two terms will cancel, okay? Because after all, t cap sub gamma s is actually gamma dot. See, t cap sub gamma of s is nothing but gamma dot of s, because gamma is a unit speed parameterized curve. Gamma dot is exactly t cap, okay? Therefore the first two terms cancel. So what you get is, from this calculation, epsilon gamma dot of s is actually equal to minus ks sub gamma dot of s by ks sub gamma squared of s, okay, into ns cap sub gamma of s, okay? So you get this, okay? So what this tells you immediately is that you see epsilon, it tells you two things immediately. Epsilon dot sub gamma of s is actually the tangent vector of the evolute. It is this scalar, which is assumed non-zero, times this vector. But what is that? That is the normal to the original curve, okay? Therefore from this expression you see that the tangent line to the evolute is the same as the normal line to the original curve, okay? So this expression tells you that this this implies that the tangent line to the evolute of gamma is the same as the normal line to gamma, okay? So this is the proof that the tangents of the evolute are normals of the original curve, okay? And see, if you think about it, you take any curve, okay, you take its family of tangents. By definition, that curve is the envelope of that family of tangents, okay? See, what is the envelope of a family of lines? It's a curve, okay, such that at every point the tangent to that curve is a member of the family of lines. So if you start with the curve and you take its family of tangents, okay, then the envelope of the family of the tangents is the original curve. So you see, what does that tell you? It tells you that you see all the tangent lines to the evolute, okay, their envelope will be the evolute itself. but they are then the same as the normal lines to the original curve. Therefore, you get the statement that if you take the envelope of the normals to the original curve, okay, they are going to give you the evolute. Okay, so it's quite straightforward. You take the family of normals to the original curve, they become the family of tangent lines to the envelope. They become the family of tangent lines to the evolute. Okay, and for that family of tangent lines to the evolute, the envelope is the evolute itself. All right, so this implies that the evolute is the envelope of normals to the original curve. Okay, so this is something you are able to see. Okay, that's one fact. Then there's another important fact that one has to see. See, if you look at this expression for epsilon sub gamma dot. Okay, you take norm of epsilon sub gamma dot. Okay, if you take norm, you see on the right side you are getting ks dot modulus of ks dot by ks squared. Okay, and that need not be 1. Of course, modulus of n cap is 1. Okay, what does this tell you? This tells you that this when you write this expression for epsilon dot gamma of s, okay, it is not a unit speed parameterization for the evolute. The point is you are writing it in terms of the arc length of the original curve. If you want to write it as unit speed parameterization of the evolute, you will have to change the arc length to the arc length of the evolute, which is not the same as the arc length of the original curve. Okay, therefore the point is that this expression tells you that whatever expression we have written for the evolute, that is not the unit speed parameterization of the evolute. Okay, so whenever you do any computations, you have to keep that in mind. You should not always assume that it is already a unit speed parameterization of the evolute. Okay, so here let me say, so I'll put this dangerous bend, caution, that the magnitude of epsilon sub gamma dot of s is not necessarily 1, because s is not the arc length of epsilon sub gamma of s. Okay, so this is a very, very important thing. So whenever you work with whenever you work with the evolute, don't directly put the don't directly apply the Front-Esserey relations. Mind you, when you apply the Front-Esserey relations, you can apply it only to a curve for which the curve has been written with respect to unit speed parameters. Okay, so that's a point that you have to watch out for. Okay, so we have this. So we have this. It's kind of now it should be quite clear that the way to go from a curve to its evolute, there are two ways. One is the evolute is simply the locus of the centers of curvature of the original curve. Okay, the other way, geometric way, is that you take the envelope of the normals of the original curve, and that's also going to give you the evolute. Okay, so there is an analytic way and there is a geometric way of doing this. Okay, and this geometric way often helps us in drawing pictures. Okay, so if you want the evolute of a curve, what you do is just draw all the normals to it. Okay, and then if you draw normals sufficiently close, then you can see in your picture that the locus where the normals are coalescing, and where the normals are coalescing is going to trace for you the evolute. Okay, so geometrically it is useful for visualization. Okay, so now we have this process of being able to go from the curve to its evolute. There is a way of coming back. Okay, to be able to come back from the evolute to the curve, there is a reverse process, which is what is called as taking the involute of a curve. Okay, so let me explain that. So the involute of a curve, but before that, let me make one more statement. If you take the case of a cycloid, okay, and you make a computation for yourself, which is very easy to do, you will see that the evolute of a cycloid is also another cycloid. Okay, so I will leave this as an easy exercise. So I will put this exercise. Okay, for the cycloid gamma of t is equal to x of t comma y of t. T is, if you want, on the real line. So x of t is equal to a times t minus sin t or t plus sin t. Y of t is equal to a into 1 minus cos t. Okay, where a is positive. Okay, if I call it as so gamma, the evolute e gamma of t is again a cycloid. Okay, so this is something that you can verify. Okay, and basically you have to use this. There is this equation that you can use. Okay, so you can use this equation. Okay, and you can verify that, right? And to show that the evolute is again a cycloid, okay, you may have to it will look like a cycloid and it is actually a cycloid. Okay, you may have to apply a translation. Okay, you will not get back the same cycloid physically. Okay, but you will get a different cycloid which is congruent to the original cycloid, right? So this is an exercise which I want you to do. It's pretty easy. Okay, but the moral of the story is that you start with a cycloid and take its evolute. You will get back the cycloid up to a translation. Okay, so in that sense we say that the evolute of a cycloid is again a cycloid. Okay, and why I am bringing this into the discussion now is because it's going to happen the other way around also. Okay, I told you that if you want to reverse this process of going from a curve to its evolute, you can take what is called the involute. Okay, and then what happens is that if you take a cycloid and take its involute at where you take the involute depends on the point, a particular point that you have to start with. If you take it at the right points, okay, the involute of a cycloid will again be a cycloid. Okay, so this cycloidal curve is very, very special. Okay, it is its own evolute. Okay, and if you take the right involute, you will get back the cycloid. Okay, and already this is something that is going to crop up. You see, when you start with a curve, when you take an evolute, there is only one evolute. All right, because it's properly defined as the locus of centers of curvature. But when you go back from the evolute back to the curve, you have to do this process of taking what is called the involutes. Okay, but when you take the involute, there are several choices to be made. Okay, and one of the choices is at which point on the curve you are going to start. Okay, and you have to start at the right point on the curve to get back the original curve. Okay, if you start at other points, the amazing thing is that you will get curves which look similar to the original curves, which are called parallel curves, but mathematically they are different. Okay, so so let me go ahead and let me define involute of a curve gamma. Okay, so the idea of involute is a very simple thing. It is that you imagine a portion of the curve from some fixed point to some other point with some fixed length, and assume that the curve is there as a string. Okay, and then what you do is you gently unwind the string. Okay, and the tip of the string will trace a curve, and that will be the involute. Okay, so the picture is like this. I have this curve. This is gamma of t. Okay, I start with, so here is there is a point p naught. Fix this point. Okay, fix this point, and then what you do is you take a, so this curve is, of course, this curve is going like this. I just take a portion of the curve. So I have a portion of the curve like this up to, let us say, a point q0, and let me assume that this length is, let us say, L. Okay, so I am taking a piece of the curve, okay, as a segment of the curve, all right, and therefore I am fixing the arc length, all right. Of course, this L can be varied, okay, but that's not the point. The point is that you fix for a fixed L, you try to analyze what this is. So what you do is that now you think of this blue portion here as a piece of string sitting on the curve, and then you gently pull this out. You gently pull this out. If you gently pull this out, what will happen is that you will get a curve like this. You will trace a curve like this. Okay, and what is the property of this curve that you have traced? Okay, if you give me any point here, all right, and you draw the tangent to this like this. So at this point, this is the normal. Okay, you draw the tangent, then you see you will get this point on the curve. Okay, and you see this length that you have, that is the length that you have pulled out. That is the same as this length that you have pulled out. Okay, and if this length is let us say S, okay, then this length will be L minus S, and therefore this will also be L minus S. Okay, and you see, if you imagine it, see, when you pull it out, mind you, you are assuming that the string is not stretchable. Okay, and you are only gently pulling it out. Physically, what this means is that the portion of the string that is pulled out, which is this, that is normal to the traced curve. Okay, this traced curve is called the involute. Okay, and I will write it as I subscript gamma, then I will put this P naught and I will put this L. So all the three choices are important. All right. This, for this involute curve, okay, at every point of the involute curve, you can see that that is the shortest distance. So if I take this point, let us say, suppose I call it as, so I will simply write this as I sub gamma. So this is I sub gamma of S if you want. All right, and this point here is actually gamma of S. Okay, you see this point I sub gamma of S and this point gamma of S, the distance between them, that is exactly L minus S, because that is the length of the string that has been pulled out. Okay, and mind you, that is also the that is the shortest distance. Okay, therefore you can imagine that this this portion of the string that is pulled out is simultaneously the tangent to gamma, and it is also the normal to I gamma. Okay, so this this segment here, maybe I should put it in a different color. You see, this segment, this orange segment, which has been pulled out. Okay, this guy is actually tangent to gamma s at of course gamma s, and in fact I should say tangent to gamma at gamma s if you want, and normal to I gamma of s, I gamma at gamma at I gamma s. Okay, and so once you believe this, okay, then you can see something. You see, look at I gamma, look at I gamma and look at the normals to I gamma. The normals to I gamma are the tangents to gamma. Okay, and if you take up the envelope of the tangents to gamma, you'll just get gamma. Therefore, what do you get? You get the envelope of the normals to I gamma, okay, is the same as the envelope of tangents to gamma, which therefore it is gamma itself. So to repeat that, the envelope of the normals to I gamma is gamma. What does that mean? It means that the evolute of I gamma is gamma. Okay, all right. So what we have done is, we have started with the curve, we have taken an involute. I am saying an involute because involute depends on some choices, all right. And you take the involute and then you again take the evolute, you get back the original curve. Okay, so let me so let me write that. This implies that tangents, normals, so let me write it like this: normals to I gamma are the tangents to gamma, that is envelope of the normals to I gamma is equal to the envelope of the tangents to gamma, and what is that? That is gamma itself. So this implies that evolute of I gamma is gamma itself. Okay, so what has happened is that you start with the curve, go to any involute, there can be many involutes, then you take the evolute, you will get back the original curve. Okay, so start with any curve, okay, then take any involute of, take any of its involutes. Okay, so of course the involute involves these choices I gamma, P naught, L, okay, is equal to I gamma. Then what you do is you take evolute, okay, you get back gamma. So you see, okay, so any curve is the evolute of any of its involutes. Okay, now you can since this taking the involute seems to undo the effect of taking the, taking the evolute seems to undo the effect of taking the involute. You can ask whether things work the other way around. Okay, if I first take the evolute and then I take the involute, okay, will I get back the original curve? The only problem is when you take a curve and you take its evolute, that is well defined. But from the evolute of the curve, when you take back the involutes, there are many involutes. Okay, the fact is therefore that among these many involutes of the evolute, there is one which is the original curve. Okay, if you make the right choice, you will get back the original curve. Okay, so so let me write that here. But again, before that, let me say the following thing. Okay, you take a you take a cycloid, okay, and you take its involute, okay, then if you take the right involute, you will get back the cycloid. That is because, you see, I already told you, you start with the cycloid, okay. If you take its evolute, it's again a cycloid that's congruent to the original cycloid, okay. And now if you take this cycloid and take its involute, you will get back to the original cycloid provided you take the involute at the right point, okay. So what you should so therefore you have this exercise which can again be written down, that you take a cycloid and you take the right involute, you will get back a cycloid. So let me write that down. Exercise, the correct involute of a cycloid will again give back the cycloid, okay. So this will happen, right? And of course, one needs to so let me say up to a rigid motion. Up to a rigid motion, in this case particularly, it will be essentially a translation, okay. And so we can also write out the formula for the involute, and that is again it's quite clear from this picture, okay. So you see, if you see, suppose I put the origin somewhere here just for convenience, okay, then I want so let me just write one line. So if this is the origin, I want the position vector of this point, okay. Oops. I want the position vector of this point, the point on the involute, okay. So I want this I gamma of s, okay. And this vector is just this vector followed by this vector, right? And so you can write out this equation. You will get I gamma of s is equal to gamma of s plus this orange vector, the length is L minus s, okay. And notice that the unit vector along that direction is the unit tangent to the original curve. So it will be L minus s times t cap sub gamma of s, okay. So this is the formula for the the involute, okay, curve. But there is a small catch here. The catch is that in this formula, again, you must notice that when will I see the way I have drawn the involute, okay, its starting point is q0. You are starting from q0, but q0 corresponds to s equal to L, okay. So the important thing here is that s is decreasing from L to 0, okay. So this is very, very important. Yes, decreasing from L to 0, okay. So that is something that you have to remember because of the way we have done it, okay. And this has to be kept in mind when you try to prove this fact, that if you want to prove the fact analytically, namely you start with the curve, take its in any involute, and then you go back to the evolute of that involute, you will get back the original curve. If you want to prove this mathematically, analytically, okay, then you have to use Frone's array, okay. And when you write analytic expressions, then you have to remember this, that in this formula for the involute, s is actually decreasing from L to 0, okay. so that you keep track of the right directions for the tangent vectors. So what I want you to do is that, I want you to write this down analytically using this expression, and that will mean that you have to compute the Frauen's-Array frame for the involute. Okay, and you have to also worry about whether mind you, the arc length is only the arc length of gamma. Okay, it's not the arc length of the involute. So the involute curve in this parameterization is not parameterized by arc length for the involute. So that is another thing that you have to also keep track of. Okay, but if you keep track of these things, you can prove the statement analytically, and that I will leave it as an exercise. Please try it. Okay, so I think I will stop here.